We are now in Chapter 10, starting with Section 10.1, Plane Figures. This first slide is giving you a definition of geometry, and then we get into mathematical systems and a little bit of history about how the Egyptians and Babylonians used geometry and inductive reasoning, but had incorrect formulas at times. And then how the Greeks approached geometry. And it was the beginning of mathematical systems, which consists of undefined terms, definitions, axioms, and theorems. And if you recall geometry from high school, you may remember doing proofs and using definitions and theorems. And so with this section, we're starting with a lot of definitions, but taking a step back, there will be some words that are undefined, like line is an example of an undefined term in geometry. And the undefined terms are then used in definitions to define other words. There are some statements called axioms that we assume to be true and do not try to prove. And then those that can be proved are called theorems. So we have a point, you have a line, notice the arrows on both ends and the points on the line so that you can name the line AB. And that's the notation. And this is the notation that you can use for lines. And when two or more points are on the same line, they are collinear. You have a plane, and this figure is just showing, like when you have a line drawn on a piece of paper, the line goes on and on in both directions, and you just have like a snapshot. With a plane, the plane goes on in all four directions, and you just have a snapshot of it. Like a piece of paper is just a snapshot of part of a plane, but it does not have any boundaries. So speaking of a sheet of paper, you're asked here to think what part of a sheet of paper could be used to model a line. Number one. Number two, could model a point. And number three, how can models of lines and points be obtained by folding a sheet of paper? So the edge could be the line, the corner could be a point, and then a crease could model part of a line. In two folds, you could have two lines that intersect at a point. When you partition a plane, you have half planes. When you have endpoints, so notice how this figure, the arrows don't go in both directions. You have endpoints, and then this is the notation you would use for a line segment compared to the notation for a line. C is the midpoint, and it bisects the line, divides in two equal parts. A ray has one endpoint and continues in the other direction. So endpoint at D and continues in the direction of E. This is the notation, notice, for writing a ray. When you have two rays with a common endpoint, you have angles. the rays are sides of the angle, and that endpoint that they share in common is the vertex. This is the notation that they use, and you can just write it like this. In other words, you don't have to have that little line inside, the little arc inside, to write notation for angles. And you can name angles by numbers or by 3 letters or just by the vertex. And then this is an example that you can do with folding a sheet of paper. So to make a ray and an angle. I'll skip through the problem-solving application. So a circle is divided into 360 equal parts called degrees. Each degree can be divided into 60 minutes, and each minute can be divided into 60 seconds. So this is the origin of dividing our hours into minutes and seconds. A protractor is used to measure angles. And a lot of protractors you'll see will have numbers across the top going from 0 to 180 in that direction. And then you'll also see some that have numbers at the bottom that go from 0 to 180 in the opposite direction. And that's so that you can measure angles no matter what direction they're facing. And so here 0 is right there. And so the angle opens up to 60 degrees. And here you can see that you have an angle that's more than 180 degrees. This, what color is that? Green arc is showing you that the angle DEF is opened up that way. So that's a reflex angle. And here are all 4 types of angles. A right angle has a box in the vertex to indicate that it's 90 degrees. An acute angle is between 0 and 90 degrees. An obtuse angle is between 90 and 180 degrees. And a reflex angle is 180 degrees. And what you don't see on here is a straight line. Don't really know why it's called a straight angle, but if you have a straight line, then that is 180 degrees. That's a straight angle. And that's more about the reflex angle. NCTM's statement about geometry in grades 3 through 5. Complementary angles, you have 2 angles whose sum is 90 degrees. Supplementary, the sum is 180 degrees. When you are teaching, I would suggest that if you're in a grade where you're teaching supplementary and complementary angles, I would suggest that you don't always use adjacent angles, which is what's here. These are adjacent angles Angles 1 and 2 share this side. Angles 3 and 4 share this side. I would suggest that you draw angles, also angles that are not adjacent. And excuse my wobbly lines. Let me draw something here. Okay. I'm going to pretend that this is 60 degrees. Okay. Let's see. What I'm showing is on the left 2 angles whose sum is 90 degrees and they are not adjacent. And here on the right 2 angles whose sum is 180 degrees and they are not adjacent, but they are supplementary. And so I just mentioned adjacent angles. And this is the first try it for this section. And so if you're doing this, sheets of paper have been folded about a dotted line as shown below. Identify each of the following angles or pairs of angles by the numbers in the diagrams. So you're using the numbers here: angle 1, angle 2, angle 3, angle 4, angle 580, angle 6, using those numbers to name the acute angles or acute angle, obtuse angle, and so forth, naming the angles there. 2 intersecting lines form 4 pairs of adjacent supplementary angles. And I have given you a video to look at that talks about vertical angles. And vertical angles have equal measure. So angles 1 and 3 are vertical angles, but also 2 and 4. So vertical angles does not mean that they are up and down from each other. They're just across from each other. So angles 1 and 3 are vertical angles, and angles 2 and 4 are vertical angles. Vertical angles have equal measure. This is a Common Core statement about geometry in 7th grade. Facts about supplementary, complementary, vertical, and adjacent angles. Use that information in multi-step problems. Name 4 pairs of supplementary angles. In figure 10.11, which angles in 10.11 have equal measure? Fold a sheet of paper to create a model of 2 intersecting lines and comparing those angles. And then here we have perpendicular lines intersect. Not only do they not only do 2 lines intersect, but they intersect and form a right angle. And this is the notation for perpendicular lines. Okay, and so this is saying segment AB is perpendicular to segment CD. Then if you have lines that never intersect, you have parallel lines. And so here's the notation for parallel lines. Line segment EF is parallel to line segment GH. Line M is parallel to line N. Line L and line M are parallel. Line T is called a transversal. And so you have your vertical angles that are formed, but you also have several other angle relationships. Here we have alternate interior angles. Right? They are alternate because they are on opposite sides of the transversal. And they are interior because they are inside the parallel lines. So angles 1 and 2 are alternate interior angles. And then you also have angles 3 and 4. They're also alternate interior angles. And alternate interior angles have the same measure. Try it 10-1-2. Fold a standard sheet of paper to model the following geometric terms, and so you can fold the paper, take a snapshot, and upload to the discussion board. A Common Core statement about 4th grade geometry. And this is a problem-solving application that you can read through. The maximum number of regions into which a plane can be partitioned by 12 lines. But I won't pause for it. I can upload the PowerPoint where you can read at your own pace. This is my first voiceover PowerPoint, so I don't know if you're able to go at your own pace or not. So I can upload the PowerPoint to allow you to do that. All right. We can draw a curve through a set of points by using a single continuous motion. You have a simple curve if what you have drawn does not intersect itself. It's a simple closed curve if it doesn't intersect and it starts and stops at the same point. C is closed, but it's not simple because it's intersecting itself. And so you're classifying each of these as simple, simple closed, or closed. So 1 is closed, 2 is simple, 3 is simple closed, as well as 4. And so you're introduced to that as we get into the name of this section, plane figures. So the union of a simple closed curve and its interior is called a plane region. So basically that simple closed curve gives you the outline of your plane region. And so they can be concave or convex. And a lot of people think of concave as caved in. The technical definition of concave is, notice how we have point X and point Y on the inside of our figure, but the segment that is connecting X and Y goes outside of the shape. So it's concave. If you have any 2 points inside of a shape and the line segment that connects them goes outside of the shape, then you have a concave shape. Even though we would be able to draw these 2 points and they stay inside, the fact that we have this one instance is enough for it to be considered concave. And that's what this definition is saying. And so if it's not concave, it's convex. So here's a convex shape. Any 2 points that you draw, the lines inside this shape, the line segment connecting them will always stay inside. And so with these 3 figures, number 2 would be concave. Okay, a circle is a special case of a simple closed curve whose interior is a convex set. So we have the tangent, which is a line that intersects the circle in just one point. A chord, both endpoints are on the circumference or the edge of the circle. The diameter is a chord that goes through the center, and the radius is a line segment where one endpoint is the center and one endpoint is on the circle. So a polygon is a simple closed curve that is the union of line segments. The union of a polygon and its interior is called a polygonal region. So it's just a fancy way to say that you have several lines that form the sides of your polygon shapes, your regions. And so the numbers of sides are given to you in the center for you to see the general name for the shapes. You have triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, decagon, dodecagon. Any other numbers of sides, it would be called an n-gon. So if it's a shape that has 20 sides, it would be called a 20-gon. Right, so you have the sides that meet at vertices. If they share a common vertex, then they are adjacent sides. And if they share a common side, then they are adjacent vertices. Or consecutive. I sometimes will refer to them as consecutive vertices. Right, so your polygons are going to be only on number 2, because number 2 is the only one that has sides. 1 and 3 have curved sides, so it's not a polygon. It's not a line segment. Any line segment connecting one vertex of a polygon to a non-adjacent vertex, so one that's not consecutive, will be a diagonal. So this is a vertex. These two vertices are consecutive or adjacent. So they're already connected by a side. So those are the only diagonals coming from that vertex, because connecting, I'm going to name these. connecting A to B, that's already happening because that's side AB. So diagonals go in the interior of the shape. And so on this try it, you are drawing sketches to determine the number of diagonals, the total number of diagonals in each shape. Next we get to triangles. So you have an acute triangle where all of the angles are acute, a right triangle where it's just one right angle, equilateral triangle, all three sides are of equal length, and all three angles. That's by default that the angles are the same measure, but so all equilateral triangles are also equiangular, but you're really going to just hear them referred to as equilateral, and so that refers to its sides. Then you have a scalene triangle where all three sides are different lengths. Isosceles where at least two sides are of equal length, so these two sides are equal. And then obtuse triangle where one angle is obtuse. Only one angle is obtuse. Quadrilaterals are four-sided shapes. So you have your trapezoid where exactly one pair of opposite sides are parallel. So this is, I'm trying to draw little arrows. Try to draw that a little better. That's not much better, but that shows parallel sides. Isosceles trapezoid, the non-parallel sides are congruent. So those are the parallel sides. And then these are the non-parallel sides, and they're congruent. Rhombus, opposite sides are parallel, and all sides are of equal length. Parallelogram, pairs of opposite sides are parallel and of equal length. Rectangle, pairs of opposite sides. So you have opposite sides parallel. And equal length. And then a square, all sides of equal length and all right angles. So squares and rectangles, all right angles. And so seeing the definitions, you can see some overlap where there are some instances where a triangle could be more than one thing. An equilateral triangle is also an acute triangle. But it's important to remember which direction these conclusions can go. So an equilateral triangle is also an acute triangle, and an equilateral triangle is also an isosceles triangle, because at least means two or three sides of equal length, but that doesn't necessarily mean that every isosceles triangle is equilateral. And then a square can be considered a rhombus because all four sides are the same length and opposite sides are parallel, but not every rhombus is a square because not every rhombus has 90 degrees. So Common Core standards about classifying and analyzing shapes. And here's more on the 5th grade Common Core standard. So try it 10.1.4, the hint is saying it may help to sketch the figures, and may also be a good idea to look at the definitions of triangles and quadrilaterals, and just, it's saying, for instance, every square is a rectangle. So look at the definition of a square, look at the definition of a rectangle, and determine if that is true. Can everything that it's saying about a square, for instance, be considered a rectangle? So there are 10 questions for you to answer for Try It 10.1.4. And then Try It 10.1.5, you're folding a standard sheet of paper to model an isosceles triangle, a square, and a parallelogram, and then justifying your answer.